We're going to start this tutorial by talking about the electromagnetic spectrum, which you see here. Notice that this side of the spectrum is the low energy side and this side is the high energy side. You always want to look for that first because sometimes they'll flip them, like you'll see on the next slide. The visible portion is what we're used to seeing, the colors of the rainbow, and if you notice, it's a very small portion of the entire electromagnetic spectrum. And so if you look at this colors of the rainbow, if you will, this is the low energy side over here. So this is low. So red light is the lowest energy. It's also the longest wavelength. And remember, that's our symbol for wavelength. Well, that one's not very good. Let's do that. There we go. There's our symbol for wavelength. And then as we get to the violet side, which is the bottom of the rainbow when we see it, that's your high energy side, as you see right here. And it's also a shorter wavelength. Okay? And then let's look at it in terms of frequency. The scale down here is frequency. And as you see, as the wavelength gets shorter, the frequency gets higher. So high frequency is equated to high energy, and lower frequency is equated to lower energy. And if you remember, when we talked about gamma rays back in nuclear radiation, they were the highest energy waves, and they also happen to be the highest frequency. And the reason that makes them so high energy is because when you have a high frequency, the waves are hitting more often because the waves are much shorter. So let's move on to the next slide. So this is the next slide, and if you notice, it's been flipped. The low energy is on this side this time, and high energy is on this side. And what we did is we just put the colors of the rainbow is what we're used to seeing in the order. Red's always at the top, blue's down at the bottom. And this is just a visual to show you what the wavelengths look like. Notice down here for radio waves and microwaves, the wavelengths are very long, but then that means they have a low frequency because it takes longer for a wavelength to hit, so it has a low frequency. So we need to remember that long wavelength and low frequency are equal to low energy, and that short wavelength with high frequency is equal to high energy. And then another way to help you remember that is you notice that visible light goes right in here, and it's right before the ultraviolet. And violet is the last of the visible light, which is the shortest wavelength and the highest frequency, and they come in right before ultraviolet rays, and ultraviolet rays are what we get sunburned with when we stay out in the sun too long. So before we start doing some of these calculations, let's talk about the first equation that we're going to be using, and that is the speed of light equation. The speed of light is a constant, so what that means, it is the same for all electromagnetic radiation, whether we're talking about radio waves, microwaves, visible light, ultraviolet, or even gamma rays. And the constant is 3 times 10 to the 8th meters per second. And if you notice up here, I tell you that they are inversely proportional. What that means is if one goes up, the other one goes down. And if you look at this equation and you know that it always equals 3 times 10 to the 8th meters per second, if my wavelength goes up, then my frequency is going to have to go down, because when I multiply them, they still must equal the 3 times 10 to the 8th meters per second. So always remember, if one goes up, the other one has to go down. That's what it means to be inversely proportional. Here we have our first example. It says find the frequency of a photon with a wavelength of 434 nanometers. So what we're going to use is this equation, what we talked about. The wavelength is speed of light is equal to wavelength times frequency, and we're going to solve for frequency. We know that the speed of light is a constant, so let's go ahead and have that ready to go, and we're going to rearrange this equation algebraically to solve for frequency. But the first thing that I notice here is that the wavelength is in nanometers and the speed of light is in meters. So that, of course, means we're going to have to convert. So we're going to do a quick conversion, and I'm going to give you that 1 meter is equal to 1 times 10 to the 9th nanometers. And that is from our very first unit. So let's first of all do that conversion. So we're going to start with the 434 nanometers And we're going to do our little grid, and we know that there's 1 times 10 to the 9th nanometers in 1 meter. Okay, so pause the video and do that in your calculator, and then start it to see if you get the right answer. So that should come out to 4.34 times 10 to the negative 7 meters. So now we're ready to put that into the equation that we have rearranged. So we're simply going to say frequency is equal to 3.00 times 10 to the 8th meters per second divided by 4.34 times 10 to the negative 7 meters. And our meters are going to cancel out. And then that is going to give me a final answer. Again, pause your calculator and see if you get the right answer. So what you should get is 6.91 times 10 to the 14th second minus 1, which remember is the same thing as a hertz. And that is your final answer. Here we have an example of finding a wavelength when we're given the frequency. And so we're still going to use that same equation. Speed of light is equal to wavelength times frequency. And we're going to rearrange it algebraically to solve for wavelength. The hertz, we do not need to do any conversions because it's meters per second, and we know that a hertz is 1/2. So all we really have to do is plug these numbers in to get our answer. So we're going to say wavelength is equal to 3.00 times 10 to the 8th meters per second, and we're going to divide that by 6.7 times 10 to the 14th seconds minus 1. And in this case, our seconds are going to cancel out. So pause the video, put this in your calculator, and see if you come up with the right answer. The right answer, if you did it correctly, should be 4.5 times 10 to the negative 7 meters. And let's double check. We need 2 significant figures because we have 2 here. So we need 2 sig figs, and so we make sure we put our answer in 2 sig figs. The next equation we're going to be using is the energy of a photon, and it is proportional to the frequency. So here you see E is equal to H times the frequency. E is going to be measured in joules, which is an energy term, and then H is Planck's constant. And that value is 6.626 times 10 to the negative 34 joules times second. And it is the same for all electromagnetic radiation, just like the speed of light is the same. That's why it's called a constant. So if you were to see that on a test as a question, make sure you know that it's the same for all electromagnetic radiation. All right, so let's get ready to use this equation. So this example says find the energy of a red photon with the frequency of 4.57 times 10 to the 14th seconds minus 1, which is the hertz. We need to keep remembering that. So this is simply plug it in and go. We don't even need to rearrange anything. So we're going to say energy is equal to the 6.626 times 10 to the negative 34 joules times second. And then we're going to plug in our frequency value of 4.57 times 10 to the 14th seconds minus 1. And we'll see that seconds are going to cancel out. So we're going to be left with the unit of a joule. So pause your video and put this in your calculator and see if you get the right answer. And the correct answer should be 3.03 times 10 to the negative 19 joules. And we're going to double check our significant figures. Our frequency was measured in 3 sig figs, so our answer also needs to be measured in 3. Remember, we never let a constant value dictate our significant figures. So we kind of ignore the H as far as determining significant figures. This time, we're going to be finding the frequency when they give us the energy. So we're going to use that same equation. Energy is equal to Planck's constant times frequency. And this time, since we're going to solve for frequency, we're going to rearrange the equation algebraically, and we're going to use this one. So it still becomes a plug and chug or plug and go. We just plug everything in. They've given us the energy of 4.89 times 10 to the negative 19 joules. And we're going to divide that by Planck's constant of 6.626 times 10 to the negative 34 joules times second. And this time our joules are going to be canceling, and it's going to leave us with the unit of second to the minus 1, which remember is the same thing as a hertz. So pause your video and plug it into your calculator, and when you do that, you should get 7.38 times 10 to the 14 seconds minus 1, or hertz. And that is hopefully what you got. Okay, so in this last example, we're going to need both equations that we've been using so far, the speed of light and the energy, because it is asking us to find the energy of light that has a wavelength of 7.80 times 10 to the negative 7. So first what we're going to have to do is we're going to have to solve for frequency. So we're going to be using the C is equal to wavelength times frequency, and we're going to solve for frequency. So remember, when we rearrange that algebraically, it's going to end up being the speed of light divided by the wavelength. So we're going to use our constant value, which is 3.00 times 10 to the 8th meters per second, and we're going to divide that by the amount of meters. They gave it to us in meters, so we don't need to do any conversions. So it's going to be divided by 7.80 times 10 to the negative 7. You know what to do. Pause the video, put it in your calculator, and see if you get the correct answer. The correct answer should be 3.85 times 10 to the 14 second minus 1, or hertz. And so now we're going to use that value, and for the second part, we're going to plug it into the energy equation. So this time we're going to say energy is equal to H times that frequency we just solved for. And so we're going to do the 6.626 times 10 to the negative 34 for the H value, joules times second. And then we're going to multiply that by the frequency that we just solved for, which is 3.85 times 10 to the 14th, second minus 1. Our seconds are going to cancel out. And so pause your video and plug that in, and hopefully you got 2.55 times 10 to the negative 19 joules. Again, two significant figures up here, so our final answer needs to be in two significant figures. And so this is just an example to show you how sometimes you have to use both equations, and you will see some like that. So make sure you know, just solve for frequency and then plug it in. All right, now for the last slide, the jokes. So for today's jokes, I'm going extra corny. What do you call a fake noodle? You call him an impasta. What's the difference between a guitar and a fish? You can't tuna fish. And then lastly, why can't you give Elsa a balloon? Because she'll let it go, let it go.